All right. Thank you very much. We had a quick change in presenter as my colleague Kaizad had to go to an alternate meeting at this time. But yes, I will be presenting our talk on autonomy in operations for Lunar Rover science and prospecting missions. So at Mission Control, we developed software for Earth, Moon, and Mars. And our two core software products are Spacefarer, which focuses on the user operations for conducting mission operations, either terrestrial analog operations or for upcoming lunar rover operations, as well as our Spacefarer AI software product, which is intended to enable autonomy by deploying AI models for spaceflight hardware. Our Spacefarer software product has thousands of hours of analog use and is now supporting missions upcoming to the moon, as well as our Spacefarer AI software now has flight heritage on 2 flight deployments at this time. One of the challenges for lunar surface science operations is really understanding the surface context, specifically for identifying hazards, being able to map and provide context for geologic and scientific targets of interest on the surface, as well as for doing instrument targeting. And so not only are these challenges to science operations, but being able to improve upon these operations will then help drive and increase the amount of science return on any particular surface mission. So what we help to develop is autonomous perception capabilities for surface mobility and science operations. And so having this capability of autonomous perception really unlocks a number of capabilities such as obstacle prediction, understanding the mobility of the vehicle that is performing the science operations, planning out like mission traverses and being able to increase the amount of activities done per unit time, supporting automated instrument targeting, identifying how the resources of the surface asset is managed, as well as how the data is managed, including science data, and being able to prioritize high priority science data for downlinking. So autonomous perception is a key enabler in being able to improve and increase the amount of science return on surface missions. So one of the products that we have developed and demonstrated is our MoonNet capability. Now MoonNet was the first demonstration of deploying deep learning AI to deep space and lunar orbit. So it is an image segmentation model that is able to identify and segment out images captured by a lunar vehicle. And there's a number of interesting capabilities that are enabled by having this onboard capability on the rover to help improve with science-based operations. So one use case, an example use case would be automated targeting of instruments. So in the first step, the rover captures an image in front of its position, and then being able to segment out the different features within that scene. For example, rocks versus regolith versus craters, can then better enable autonomously targeting based on the type of feature that it sees. So for example, a crater might be of interest for identifying if cold trap potential, and may be used for auto-targeting a thermal IR imager. Whereas a rock or a boulder might then have interest in characterizing the mineralogy of that feature, and could then automatically target some kind of multispectral imager, and also could provide automated targeting for a LIBS instrument. So having this ability to automatically segment out images within the scene can help improve and enable autonomous targeting to help increase the science return. Another potential example of this capability is downlink prioritization. So when the mobile platform or the rover has the ability to capture more images than can be downlinked by bandwidth constraints, a system can segment out and identify those features within all of the image sets, and then be able to identify and rank those features and prioritize them for downlink. So, for example, if downlinking or identifying craters is a high priority, then those images with crater features or a greater number of crater features would be prioritized and then downlinked. And then, so this would be useful for example, like identifying strategic decisions for prioritizing certain novel features and key science targeting. Another use case would be supporting operations for science teams by being able to pre-annotate images on the ground. So when the science team is on the ground is looking to conduct operations and prioritize what their next course of action would be, being able to pre-annotate features within a console to better communicate with their operations team members their intentions for which features they want to pursue and target. This is just an enabling feature that helps to improve the process of operations and increase or save time during that process. So one key demonstration of this MoonNet capability was recently demonstrated as part of our Lunar AI demo. We were a payload customer on board the recent iSpace Hakuto mission, and so our small form factor spaceflight computer was integrated onto the iSpace lander, which successfully launched and entered lunar orbit. There was a landing attempt, which unfortunately was not successful. However, we were able to demonstrate that our MoonNet payload was operational in lunar orbit. This was going to be demonstrated in collaboration with the Emirates lunar mission. So our MoonNet payload, which was hosted on the lander, would be performing its segmentation on images captured from the Rashid rover during its operations. So unfortunately, we weren't able to do that in-flight demonstration of that capability. However, it was still a significant success in demonstrating that it was functional in lunar orbit, and we do greatly acknowledge the support provided by the Canadian Space Agency for this capability demonstration. The way we envision this capability being deployed in this architecture would be the rover capturing images. Those images would have been classified on the lander, the data downlinked, and then having those segmented images available to the user would then help identify and improve the decision-making capability of science team users interested in furthering their science capabilities. So another capability that we are advancing and demonstrating is our spacefarer operations software. And so this is what allows users to operate their mission. And so this has been developed out of lessons learned through thousands of hours of analog missions with science users contributing and defining the types of features that they want to use out of an operations software. And our most recent demonstration of using Spacefarer was at the ESRIC Space Resources Challenge. So Mission Control participated in the Space Resources Challenge. So we were one of the 13 participants that participated in the 2021 challenge in the Netherlands. We were then invited back as one of the 5 finalists in the 2022 challenge in ESRIC. This was an analog environment in which us as a team were able to use our Spacefarer product to operate our rover in an analog setting in which we had 5 in-person team members on site in Luxembourg, as well as 3 remote operators, all able to view and participate in the mission using this software tool. So our integrated system was fully integrated with Spacefarer. We had 2 instrument partners providing path to flight lunar instrument prototypes. And those were integrated onto our COTS rover with standard GNC sensors. We had a LIBS prototype that was loaned by Impossible Sensing, as well as a LiDAR sensor prototype loaned from MTA. And so we integrated these into our system for conducting this lunar prospecting analog mission. And so it just shows the capabilities of being able to integrate in different instruments into the software platform for conducting lunar science and prospecting. Our approach was basically really focused on operational readiness and having our system available in our indoor lunar facility, integrated with all the hardware pieces, and as well as Spacefarer to enable remote participation and remote operations, really helped improve our operational readiness through an analog setting, which we believe is critical to successful lunar missions and lunar operations. We really do believe that high readiness is key to success. So just in quick summary, our belief is in Spacefarer and Spacefarer AI as tools for helping improve lunar science autonomy and lunar science operations. And so thank you very much.